Hey everybody, today we're going to be talking about congruent polygons, and yes, by the end of today's lesson, your favorite, the proof, will be back. So by the end of this lesson, you will be able to identify congruent figures and use corresponding parts to find angle and side measures. So what is a congruent figure? Well, congruent figures have the same shape and size, meaning that their corresponding parts are equal. But for me to use that definition, you have to understand what corresponding parts really means. So corresponding parts means that the angle's in the same location on each figure. So if I'm looking at two triangles, for example, an angle on one figure corresponds to an angle on another figure because they're in the same location on these congruent figures. Same thing with the sides. The sides are in the same location on each figure. So if I were to look at these two polygons, in this case some quadrilaterals, ABCD and PEST, and I'm told that they are congruent, what does that tell me? Well, I can look at this congruent statement, and it's kind of neat. It tells me a lot of information. AB has to be congruent to PE, so I can mark AB and PE. BC will be congruent to ES. CD is congruent to ST. And by default, we can probably figure out that AD is congruent to PT. But if you look, AD is congruent to PT. Now, those are not curves like I'm trying to show you an arc, but instead I'm just showing you that those two items, being at the front and the back of their naming of these polygons, also form two congruent segments, okay? Where that's helpful is, as you can see, these two polygons are not necessarily going in the same direction. And while these are fairly obvious, sometimes figures can be drawn in such a way that they're not as obvious. So it's kind of nice to be able to look and see, using that congruent statement, where the congruent pieces are. It not only tells me about the sides, but it also goes and tells me about the angles. A comes first, P comes first. So angle A would have the same measure as angle P. B and E would be the same. C and S. And finally, D and T. If you can manage to get 4 things drawn, as I'm obviously struggling with. Okay, there. Every time it's landing on top of each other. But you can see that those help me find those corresponding pieces as well. So it helped me not only find the angles, but it helped me find the sides, all from one simple statement. This would also help me in drawing them. It might not tell me what its actual side looks like, but it would help me to recreate them simply by having that simple statement. So now, if that's the case, looking at this, can I create my statement of congruence? Meaning, let's look at the pictures and go from there. So if I look at this, depends on if I want to go from angles or if I want to move from sides. But if I started with my sides, start here at A, C, T. So triangle A, C, T is congruent to. Now notice I started with A, so I'm looking at the 3, and then as I moved up, I went along the 1 and ended where the 1 mark was to C, so that would put me at O, D, G. So triangle O, D, G. Now I could have just as easily named these triangles differently. I could have went with C, T, A, and D, G, O. Doesn't really matter. I went off of sides. The other way that I just mentioned would be going off of angles. Doesn't matter as long as the corresponding pieces are together. So AC is with OD, as it should be. CT is with DG, as it should be. And AT is with OG, just as it should be. As I look, A has the same measure as O for angles, C corresponds with D, T corresponds with G. So all of that makes sense, and it's in the correct order. Now we can move beyond just knowing that we have the way of naming these conventional things, but we can actually use the fact that they are congruent to actually determine variables. So based off of this, A would be corresponding to S based on what it gave me. We would hope with something like this you would have a congruent statement, but if A is congruent to S, that tells me that 52 is equal to 2x minus 12, or 64 is equal to 2x, or 32 is equal to x. Likewise, I could then say that BC is congruent to RT. Now, at first glance, that's not a pretty thing because it says 3y minus 13 equals 1/2 x plus 4, but that's okay because we know what x equals. So we'll just substitute that. So 3y minus 13 is equal to 16 plus 4, or 3y minus 13 is equal to 20. Or 3y equals 33, and y equals 11. So even though we had one thing involving a y and another involving an x, because we were smart and solved for x at the beginning, nothing became a problem for us, okay? So, like everything that we seem to come up with, there's what's known as the third angle theorem, or third angles theorem. I think it's supposed to not have an S there. If two angles on one triangle are congruent to two angles on another triangle, then the third angles are also congruent. Now you may say, why does that need a theorem? We know that angles add up to 180 in triangles, so if two of them are already congruent to two on the other one, it stands to reason that would be the case, but we do have a theorem that says it. And anytime a theorem comes up, we know that we can prove it. So that's exactly what we're getting ready to do. All right, so it says angle R is congruent to angle H, and angle S and angle J are right angles. Those are our given statements. Our goal is to prove then that the third angle, T and I, are congruent. Now again, we're going to prove it so that we know what's going on. So let's start with our givens. Angle R is congruent to angle H. They've already listed my second given here in statement 2. Otherwise, I could have put it up in statement 1. So that means that this is just a given as well. Now they said angle S is congruent to angle J. Well, we've only identified that they're right angles, and that's just definition of right angles. And then for definition of congruent, well, if we know that we have these two sets of congruent angles, then we know the measure of angle R is equal to the measure of angle H. We also know that the measure of angle S is equal to the measure of angle J. That's what's true about any congruent angles. Also, using the triangle angle sum theorem, we know that the angles of S, R, and T add up to be 180, and also J, H, and I add up to be 180. Now we already know that S is congruent to R and J is congruent to H. So if we substitute in this whole statement that's equal to 180 and this whole statement that's equal to 180, we can say that the measure of angle S plus the measure of angle R plus the measure of angle T is equal to the measure of angle J plus, that is a plus, the measure of angle H plus the measure of angle I. Please forgive my not so great handwriting. So take the 180 out. We could probably have said transitive as well because we're taking out the middleman, but substitution works well here. Subtraction property of equality. If we take out all the things that are equal, S and J, R and H, what we're left with is the measure of angle T is equal to the measure of angle I. And if we have the measure of angle T equal to the measure of angle I, then we know that angle T has to be congruent to angle I, because that's the definition of congruent angles or anything. And what we have is now exactly what we were trying to prove. All right, that's it. Have a wonderful day.